Welcome to this session on optimization. I'm hoping those people online can hear and see us. Ben Jankowskis, can you sort of give me a quick wave? Recognizing somebody here. Well, never mind. Anyway, unless they say otherwise, I shall assume people are hearing us. We've got 4 presentations. So the first presentation, Luis Fernando Garcia Rodriguez, if you'd like to tell us a bit about your work.
Okay, so hello everyone. Well, my name is Luis Fernando Garcia Rodriguez. I did my PhD at the University of Sao Paulo. And I have worked along with Professor Emilio and my colleague, Diego Ayashi. We are part of the Research Center for Greenhouse Gas Innovation from Shell Oil Company in Brazil, where we developed several projects related to sustainable energy. Yes, so I would like to present you part of my PhD work that is labeled Design of Rotors under Turbulent Subsonic Compressible Flow using Topology Optimization. Okay, so just a little quick view about the University of Sao Paulo. Well, I'm not Brazilian, actually I'm Colombian, yes, but I arrived there at Sao Paulo. It's a large city with more than 10 million people. And the University of Sao Paulo, it's in the, well, it's like almost in the center of the city, yes. Is ranked as first one in Latin America, and inside the university there are different research centers, as the Research Center for Greenhouse Gas Innovation from Shell Oil Company, where I'm part of, where we are working over there, almost like 300 researchers from all over the country, and also we are also working with people from the Imperial College as well. So next one, Professor, please. So these are the contents of my presentation. At first, I would like to give a first introduction about the work, please. Next one. Part of the program in order of CO2 carbon capture and storage management, where the goal is to optimize the performance of such technology, and we do it by means of optimizing the performance of the compressors stage systems, which consumes around 5% of the power plant. So the goal or the basis of this research, it was about optimize the performance of the rotor at first, yes, using topology optimization techniques. So, well, as you know, there are different kinds of optimization of fluids. We have like parametric optimization. Modify like the initial dimension of the initial sizes. We also have got some shape optimization where we can change a little bit the boundary to optimize the physical performance. Yes. And finally, we got topology optimization where we actually modify the region where the fluid flows in order to get or achieve the unexpected goal, yes, optimize the energy performance or minimize the energy dissipation across the whole domain. So how do we do it? Well, we just, in this case, what we do is to penalize the governing equations. We basically change the permeability of the cells domains that are inside space, and we define if the cells inside the domain should be either fluid or solid in order to achieve so can you press next one, please? Thank you, Professor. And next one, please. Okay, so you can see here how the process goes. We have an initial domain, for example, a straight blade rotor. And we focus, for example, in one part of the rotor, yes, which is discretized either by finite volumes or finite element methods. We develop the topology resolution of the system, and we have an optimized topology, which is then post-processed and built in experimental. Yeah. So thank you. The next one, please. Rotors optimization. Some words have been developed compressible regime mainly, yes, especially for non-Newtonian and Newtonian fluids, yes. But when we talk about compressible regime, well, I remember when I started my PhD, there was nothing about it. Yes. And recently, this year, 2 works have been published about topology optimization of compressible flow, but for low Reynolds numbers, yes. And the goal was to develop all the basis for turbulent regime, yes, high rate optimization for rotors. So that's as next one, Professor. Thank you. So as you can see, this one, which it summarizes basically in order to develop topology optimization for compressible turbulent regime. Yes, in order to optimize the performance of rotors, specifically for the CO2 carbon capture and storage management program that is developed over there in that part. That's the main objective and goal from the current research. Well, now the difference between this work and the previous one, besides the regime, yes, that we are reaching for high Reynolds numbers, is the discrete adjoint approach in order to adjoint code. Yes, we're working with finite volume, finite element methods, which that I showed you, and we are working on the subsonic regime. Okay, being that said, so I can show you here now a little bit about what we did is to minimize the energy dissipation through the Fans equations for rotational steady flow. We have used also the modified turbulence model, the Ray-Agarwal turbulence model, and everything has been implemented in a software that we developed before. It's called.
Sounds really bad on the.
Oh, okay, thank you. Okay, thank you very much. Everything is now implemented, which is software OpenFOAM advantages with Phoenix advantages. Probably know our primary states equations through OpenFOAM. The results of OpenFOAM to a Python. And by doing so, we have been able to reach actually the trickiest part of the compressible flow here in topology optimization, getting the adjoint code. That was like the trick over there. So here you can see the previous formulation that I showed you. Yes. Equations, the modified everything. It was for the Fans equation. We have implemented the library adjoint, which basically, as you know, we have our model. Yes, differential equation where the private variables are represented by U and the optimization parameters are represented by M. Everything is inside of analysis space. The functional of the previous formal model can be yes, this is basically when we put the forward model into the functional. So okay. So, well, basically, the idea of using the automatic differentiator is to make some symbolic operations with the matrices in order to help us to get the functional gradient by a sequence of orders, yes, without using the hand derivation of the continuous adjoint approach, yes. So, well, we use that from Phoenix, yes. So we couple OpenFOAM and Phoenix, we solve our adjoint equations, and after we take our topology optimization formulation and generate the Lagrangian, and we make some Fresh-Check derivatives with respect to the primal state variables of the states, we can calculate its sensitivities, yes, and we use the IP-Opti optimizer in this case in order to get the final local solution of the nonlinear program. Here is, and we check a conversion criteria. So if we reach if we haven't reached our conversion criteria, we update the material distribution by following this material formulation that we have make it separately for each one of the equations. I mean, we have used one material distribution for the momentum equation, another one for the energy equation, another one for the turbulence modeling. And after everything is checked, well, if it converges, now we got the optimized topology. You can see a little bit more about the methodology, yes, about the Phoenix OpenFOAM software, this resource that was published last year. Well, it was an incompressible regime back then, but I mean, the methodology of the Phoenix OpenFOAM, you can find it there if you want to see a little bit more about how does it works. So what we did was taking that to compressible regime. So at first, well, a lot of discretizations were made. So these results that I'm showing you here are for subsonic flow, perfect gases, isothermal walls. For the Spartan malars, we use for the channels optimization, the Hrvoje for the rotors optimization. We have used the Fans equation, the positiveness hypothesis as well, in order to get well, these results. So before moving forward to rotors, of course, the challenge, okay, I mean, the challenge was first, let's try to optimize a channel. As soon as we optimize a channel, then we are able to optimize a rotor. So we took this real geometry, yes, and we optimize it. So as you may know, when we are kind of using this kind of diffusers, well, we could get some vortices at some parts, yes. So the goal is to diminish that energy dissipation, those vortices generation, yes. So by applying the previous method that I showed you, yes, and specifying especially the inlet and outlet boundaries as a constant pressure in order to allows that the pressure gradients be maintained at the diffuser, we were able to optimize it, yes, at this final topology that you can see, where the black region is now represented by solid cells, and the white region is represented by fluid cells. And as we saw, okay, we have now a thinner channel. It still guarantees the pressure difference between the inlet and the outlet boundaries, and we are reaching at the subsonic regime. You can see more about channels optimization of compressible flow at this submitted paper that we published, that we sent like recently. So another important fact of using or developing the base topology optimization of compressible flow is about not only guaranteeing high velocities, but also as you can see here in the density fields, the variations are large enough in order to be feasible to get, I mean, or that justifies the uses of the compressible solver, because, well, some questions have been asked about the topology optimization community that, okay, let's make the optimization with an incompressible based solver or compressible regime, and it is not a good approximation. Yes, I think I have here some results. Now with rotors, so at first I took this also real rotor, yes, published at the literature, a straight plate rotor, yes, and we optimized its cavity, yes, and it's going at 4,000 RPM. So Again, the objective is to minimize the energy dissipation between the inlet and the outlet boundaries. And well, you can see here how the topology was solved and how it is the optimized rotor projected. Yes, again, the solid regions are represented by the black part that you are seeing over here. Again, we're reaching Mach numbers of subsonic flow. Yes, we are putting some solid cells inside the fluid cavity. Yes, and of course, the dissipated energy between both domains is way different. So we were able to minimize the energy dissipation of this case. So finally, I will show you a 3D example. Yes, through the 3D examples, one radial rotor. So we extended the domain from the initial one that I showed you previously. Yes, and we check here the influence of the boundary conditions. So when we were using wall boundary conditions, some reverse flow was seen at the tip of the resolution, which was something that we were not looking for. So when we changes the boundary conditions to cyclic one boundary conditions, we were able to overcome the mentioned problem. Yes, until we got like a Tesla-like pump rotor that we have optimized over there. You can see the result here, how the topology changes along the iterations, how the energy the energy dissipation is diminished until we got our conversion criteria. Okay, great. And finally, okay, let's make an optimization of a mixed rotor. Yes, axial inlet, radial outlet. We extended the initial domain in order to allow the optimization to be be performed. Yes, that's something that we do in topology optimization. We extend a little bit the domain in order to let it freely goes. Yes, and not be subjected to some original constraints. And well, here the time processing will cost a little bit more. Yes, and we are using the triangular meshes because we are converting these cells into Phoenix. Remember, the Phoenix is a finite element based software. That's the reason why we're not using the triangular meshes. Until the end, we got the following project rotor. So basically, the conclusions of this work is that we were able to optimize rotors under compressible turbulent regime. Yes, the Fans equations have been accurately used along with the luminosity hypothesis for topology optimization. Firstly, the energy dissipation function it worked properly, but we can also check another different objective functions at the Phoenix OpenFOAM software, because it allows us getting the adjoint code without any handmade derivation. So, for example, we are also testing minimize, for example, the entropy generation and so on in other tests that we are making over there. And well, we can see that especially the location of solid cells in critical location, for example, when the vortices are generated, it has helped us to improve the energy performance along this domain. So, well, basically, I would like to again to extend my acknowledgement, sorry, miswritten, to Shell and to Compressible through the Sao Paulo Research Foundation for having sponsored this research. So, thank you very much for the time. Sorry by the inconvenience.
Okay, there's time for some questions online or in person. Yes.
Yeah, so very so this might be a slightly famous question. Why not do everything in Phoenix?
The question, by the way, is why not do everything in Phoenix itself?
Okay, yeah. Well, Phoenix is quite good developed for topology optimization of structures, yes, but it is a finite element based software. There have been some tests already run in 3D dimensions, but as we already know, the finite element method does not acquire so properly the fluid mechanics as its finite volume does. Yes. Also, OpenFOAM is an already developed and stable software for fluid flow, so we are able to reach different libraries that are already written in OpenFOAM. In Phoenix has got nothing about it. I mean, we did a compressible solver in Phoenix, yes, for the fancy equations. But for example, when we want to work with real gases, when we want to work with more other turbulence models, and everything has to be like again written in Phoenix, it's not as easy as just use it already in OpenFOAM that is already implemented. So the first works that I show you here, they were made in Phoenix, yeah, through Phoenix and using the finite difference method, but they were only for laminar regime. So now when we are working with turbulence regime, we say, okay, OpenFOAM is way more developed, so let's use it and combine it with Phoenix. Let's move it forward.
Can I ask a follow-up question?
Yes, sure.
As I understand it, you've written your own coupling between the two codes, but there are a number of existing open source solutions there, like Precise, like MUI. Why did you write your own where you could have used some off the shelf?
Yeah, for example, there is the DA-FOAM, yes, which is an automatic differentiator that is being developed for OpenFOAM, but it's basically for shape optimization, right? So, well, sometimes it's easier to write your own code than modifying an existing code, yes, but it is also a good strategy. Also, one of my colleagues, actually, he's changing DA-FOAM for topology optimization applications. Okay. But well, when I was doing that work, I found it easier just to couple it with Phoenix, and it's another good strategy, but I took the first one. Instead of understanding and changing a whole complete code and say, okay, let's make the interfacing. That would be easier for me.
Are there any other questions? If anybody online wants to unmute themselves or type something in the chat. Okay, well, thank you very much.
Okay, so good morning, everybody. Welcome to my talk. I'm Markus Towara. I'm a postdoc at Aerodynamic University in the group Software and Tools for Computational Engineering. And this is like a little bit of a twofold talk. I'm going to show you what we did with Discrete adjoints in OpenFOAM. Then I'm going to show you some results from a project we had, which was like an industry project for KMUs, funded by the German government, where we worked with Isatec Aachen and Cloud and Heat in Dresden. And we did some examples on conjugate heat transfer. But let's first start off. And I want to start by basically doing kind of a summary at the beginning. So you know what our plan is in this presentation. So we as an institute, as the CE, we develop AD tools, and we maintain a fork of OpenFOAM with AD enabled everywhere, basically. We have adjoint, tangent, so reverse or forward mode implementations in there. If required, we can also nest these to get higher order derivatives. So I'm going to motivate that adjoint AD gives you accurate derivatives at a comparatively cheap cost. So it's not free lunch, but it's much better than doing like time differences or something like that. Yeah, and so this the results I'm going to show you come from this project here, which basically says adjoint methods for optimization of cooler geometries in cooling cloud computing resources. Okay, so we already heard from you and also from you yesterday about topology optimization, so I'm just going to keep it short. I've been showing this slide here for years, just as a motivation thing. Why would you have big gradients in your code? Well, we have some initial geometry. We want to optimize it without necessarily remeshing all the time. So we introduce this penalty term in the Navier-Stokes equations. So we're just stop using this as a point. We're keeping it simple, and doing the classical porous media approach, where we just add this minus alpha u term at the end, which you can by like rearrange a little bit as a Darcy porosity. If we crank this parameter up to something big, we can penalize the flow, so it won't go through there. And if we don't, if we keep it at 0, then we basically leave the geometry unchanged. And we cap it above 0, because if we leave it below 0, then we would kind of have a momentum source, which in some applications might make sense, but not like in this general approach here. So we have a constraint optimization problem, and every cell in our domain can be optimization parameter. So we have a very big field alpha. And yeah, if we're done with that, then it might be a good idea to throw away this topology optimized geometry and actually do a correct remeshing, because right here we don't do any inverse boundary or whatever. So the influence of the wall is not the real physics. So it's better to retest it in a reparameterized way. Okay, then we have to define, in order to get a gradient, we'd have to define some kind of a cost function. So it could be like a power loss between inlet and outlet. It could be in conjugate heat transfer. It could be some temperature difference. And once we have that, of course, the big question is, how do I optimize that? And yeah, if I don't want to do like stochastic methods which don't need gradients, I need a gradient. So the question is, well, what we're going to discuss, how do I end up with this gradient? And if I have it, then I can do something smart or something stupid. So we were just doing something like very basic, doing the steepest descent upgrade step, like typical Rosenberg example. You just walk in the direction of the gradient. Of course, Rosenberg is really bad for that, but this is just as an illustration. And then, of course, you could do something more clever, like interfacing with IPOpt, like you did, or using some other scheme which maybe even needs second derivatives. Okay, then we do this update step until we get a converged alpha, hopefully. Okay, but now, of course, the question is, how do we end up with a gradient which we can use? We have multiple ways of getting that. One, of course, where the basic approach would be finite differences. And if you go through your whole simulation, in general, there's no sparsity to be exploited there. So you will need, if you have n cells, you will need n evaluation of your finite differences model. So it's extremely expensive. Same for the forward mode of AD. If you don't have a sparse stencil, then it's the same complexity as finite differences. But with Adjoint-Based, we can get down to the complexity of the output dimension, which here usually is 1. So by calling our adjoint model once, which of course might be a very expensive adjoint model, we can get the gradient, and at least it's not as expensive as doing the full thing. Okay, so how can you get adjoint sensitivities? So now we just assume that we know what that means. There's two ways. There's this continuous adjoint method where you derive the governing equations for the adjoint on paper, implement it, and then solve these equations along the primary equations. So that's something which, when we started, was still a thing which only lived at Volkswagen, I think. But now it actually is in OpenFOAM and is usable, and there's stuff added more and more, which is rather exciting. So that's the continuous way. The good thing, once you did all the like error-prone and really hard, and I couldn't do it fast, you have something which is fast, and also you can look at the physics of it. But yeah, the downside is a little bit hard to derive. And also for some like complicated stuff, like for turbulent models and something like that, there can be inconsistencies to the primary. For the discrete adjoint model, so that means by automatic differentiation, is we just take the primary model and differentiate the code. So if we have a million lines of code, we just differentiate each of these lines basically, and use that to get our adjoint. Good thing is it's very flexible once you've done it. It's automatic, and the sensitivities you get, well, at least you know that you're consistent to what you have implemented. Of course, if what you've implemented doesn't capture the reality really well, then a little bit out of luck. Yeah. The downside is it's generally rather memory intensive because you have to do a control flow reversal. You can only start to, so the machine learners would say backpropagate. We usually say reverse propagate or something like that. You can only start reverse propagating adjoints once your computation is finished, and you need the intermediate states as well, at least some of them, in order to do this propagation. So in general, it will be slower than the continuous. Okay, so some words of about AD. So here we are using the notation by Andreas Lehmann, who's kind of the godfather of AD, at least in our field. So we have the forward mode of AD, which is like the more intuitively interpretable. You got the gradient here in this example. You are allowed to multiply it by some tangent, so this x dot we call tangent, and you're free to choose whatever this tangent is supposed to be. So if you want a full Jacobian, or let's say let's just stick with the gradient for now, then you would seed one unit vector and you would get one entry of the gradient. And so of course to get the full gradient you would need to do that n times. And so the reverse mode is this rather peculiar piece where you do that as well, but what you stick in is not an input tangent but an adjoint of the output. And then somehow it will be transformed, and if your model has evaluated, you can get the derivatives from the adjoint of the input. And if you have a scalar output, you just have to call this function model your implicitly defined code once to get the full value. Okay, so if you are in a mode where there is sparsity involved in your computation, you have something which is a matrix, or Jacobian, or Hessian for higher order, you can do exploitation of sparsity by coloring, basically compressing your Jacobians and Hessians so that they are not square anymore, and then you need less rows or columns to compute. But that's something we don't focus on. Okay, so now we got this technology, and let's just assume we as an institute have an AD tool. And so we do have one, luckily. What can we do? So we dropped that into the OpenFOAM.com version several years ago, and whenever there's an update coming out, I'll basically reserve like a day or two and do a pull, and then we get everything inside our repo. We use an operator overloading AD tool. So there are two different thoughts about AD. There's source code transformation, where you take in the code, do some AD magic, get out both the primal code and the code for the adjoint. In general, of course, this is really cool if it works, but it does not generally work for like high order languages if it's a general purpose language. So if it's a DSL, then it's very much possible. But for C++, for example, it's very hard. There are approaches like Enzyme, where they not differentiate the actual language, they differentiate the LLVM backend. So they use the power of the LLVM compiler, and then write back differentiated LLVM code, which will then be differentiated with slang. So that's also rather cool, but I think that's not prime time ready yet for a code like this, because basically everything has to be in one single code base. You can't have, or it's hard to have multiple translation units and stuff like that. But then for operator overloading, the idea is you have a custom data type which is able, it is able to propagate both primal value and also like a tangent or an adjoint in some way or form. So that's what we did. We changed the central OpenFOAM type def to our data type. So we did that to everything in source. So all of the libraries basically have it in there. And then, of course, doing all the applications, we maybe care about 5 of them, we didn't do it, but we have basically a subset of applications, and the usual ones that work. And if you then want to actually write an application which uses sensitivities or derivatives, what we usually do is we just copy one of the existing solvers, for example, simple form, call it adjoint simple form, and then put in some of our glue to get the derivatives. Yeah, so what we did. Our tool here is called AD-HBP, which basically, so our tool we developed at the Institute is not GPL. So what we did is that we created a version of that which was GPL friendly. Okay, so currently, because I didn't put much time into it, we have no good interaction with the optimization capabilities which recently came into OpenFOAM. So I would very much like to change that, but time is sparse. Okay, so what are the benefits and the disadvantages of having Discrete Adjoint-AD directly in OpenFOAM? Well, it comes at a cost because you do all the operator overloading. You have to do memory allocation for the control for reversal. So you need to store these intermediate values. And then you actually have to do the reverse propagation also. That takes time. In general, the runtime will be increased by something like a factor of 5 or a little bit more, depending on what you do. Remember, we had to replace all of our floating point variables by our data type. So unfortunately, OpenFOAM does not have a type def for the data type. No, it's not templated in the data type. It's only a type def. So it's easy enough to change it, but it's hard to have multiple versions of, for example, the solvers and stuff like this. So we can't have just double the. So it's hard to fall back to double implementations. One crucial thing is that you don't have the idea to differentiate through the linear solvers because that's numerically hard. And also, if you do a lot of iterations, then this will clog up your memory pretty much. So we instead do that analytically. And we retain parallelism by adjoint MPI. So there's a library called AMPI, which tackles that. So we still have the parallelism in that. Okay, then now we have the AD in OpenFOAM. What other features do we use for getting that efficient? If we want to do a full simulation run, because for example, this simulation is unsteady, there has to be some kind of checkpointing because else you won't be able to fit all the time step into memory. So we implemented that, the checkpointing. If it's steady, you can instead do reverse simulation. So you only tape the last iteration step and then repeatedly reevaluate that. Or you can one-up that and do instead piggyback optimization, where then also you already use your not converted gradient to also do a design update, so change your parameters. And then also with something which we, in my opinion, don't do enough. So we as an institute, all the other guys are doing it. For the steady case is that you do the implicit differentiation of the residual. So that you don't actually tape through a time step, but only through the residual. And then the implicit function theorem tells you how to then obtain the derivative of your design variables with respect to the your parameters. So that's the XDA. And then you have to just multiply that by some other term which comes from the cost function. Then you're done. So I think this is what DA form does. Okay, now let's shift gears and look at some applications. So we had this product with Cloud, as I told you. They built like individual cluster solutions. So this is just like an illustrator picture on how such a blade could look like. So they're doing water cooling. Cool water comes in, hot water comes out. But because they want to use the water, for example, for heating a building or something, they don't just want to waste the energy. The inlet temperature already is rather high. Okay. So in this project, the share of work was like this. We as an institute developed the actual optimization stuff in OpenFOAM and ran the simulations. EtherTech, which is a engineering consultancy business in Aachen, did a lot of verification work with Siemens Flow EFD. We also did a lot of constructive stuff with like solid mechanics and whatever, how you actually fix the cooler you developed to the bigger picture, because it turns out like there are different heat expansion coefficients, and then you want to glue it in there, and then it becomes brittle, stuff like that. So that in this direction, and then Cloud and Heat designed and constructed a test chamber for which we could then verify the results. Okay, and so for that we decided to look into conjugate heat transfer with OpenFOAM. So what's the challenge here? Well, we have potentially at least we have the cost function defined on a completely different region than the variables we want to optimize. So the cost function could live in the fluid region, the variables to optimize could live in the solid region. And so we need to transfer the sensitivities through the mesh coupling and the interface. If you decide to differentiate through the whole iteration history, then of course it becomes an issue that the convergence of the temperature isn't as great as you would like for conjugate heat transfer, at least before these new features came into OpenFOAM. So that becomes really expensive. The meshes between solid to fluid and fluid to solid interface does not have to be the same. There's interpolation going on, and so you also need to be able to differentiate through that. So then on a more technical thing, we have the problem that the boundary conditions used for conjugate heat transfer have data members which are not present in the base classes which they derive from. Of course, that could have happened to us for all other boundary conditions as well, but we never had one before. So that was a bug we had to change because we only checkpointed the data from the base class and not from this derived class. So we had to do some special handling for that. And if you want to do topology optimization in there, so we want to place material which kind of resembles the solid region, then of course you have to replicate the physical properties of the solid domain inside the fluid domain as well. And so we had some troubles with that, but actually I read something on Hrvoje yesterday, which I'm very much excited to investigate on how to get that done easier. Okay, so what did we actually do? So these are just some results. First, before we started our adjoint simulations, we did just some design exploration, just played around a little bit with parametric simulations. So what I did is that I generated my geometry with OpenSCAD. I'm not entirely sure how familiar you are with all of that. So that's something which is really popular for some reason in 3D printing, because I think Thingiverse supported it early on. And this will allow you to export an STL, basically, but not a step. Then I had to do some post-processing or pre-processing, however you like that with Python, in order to split that STL up again into something where I can apply boundary conditions for CF mesh. Then we did the meshing with CF mesh, simulate with conjugate heat transfer, not reach in simple form, then glue all of that together somehow with bash. And then we're able to explore a parameter space of these ribbed coolers there, where we also had some kind of draft angle on the ribs, and also these pin coolers there. For the pin coolers, we decide, okay, the results, in terms of heat transfer, are really cool, but we can't afford the pressure loss we get in order to get competitive with the rib cooler. So we decided to just carry on with the rib cooler. And then we did adjoint simulation to reduce the complexity, because we saw that if we had this uniform spacing of ribs, it didn't matter too much where you were on the die, if you were in the center line or off center. So we just set up a single rib with symmetry conditions to both sides. And you can also see there that we filleted the edges a little bit, so that we don't get sharp normals if we want to do a shape optimization. So here we are doing a shape optimization which means that we move the individual points on the surface mesh. And if you don't have sharp edges, then it becomes a little bit hard to interpolate and decide what to do with it. Yeah, so here you can see what we have. We have some regions with a positive selectivity, which means that we, in this case, flipped. But I think we pulled it out, and that some regions we pushed it in. And yeah, so we simulated that. I must say I'm not entirely happy with these results because the gains we got by that were a little bit inconclusive, and we were not able to verify these results in the test chamber because of COVID, and we didn't get these things manufactured quickly enough. Whatever, we couldn't actually test it. But at least we see that we get sensitivities which look decent, and we can apply this to a mesh morpher in order to get a optimized geometry. Okay, so that's the end. Summary: with AD, you can get efficient and accurate computations of derivatives directly in OpenFOAM if you want to. We applied this thing to problems. Okay, so if you want to apply this technology to your own problems, I invite you to visit our website. There's a short link there, or just hit me up, email, LinkedIn, whatever. We give you that stuff. It's just behind basically our GitLab wall, so that we don't get like a bunch of strangers on Google and I have to do support all the time. But if you just ask us, we will give you access. Okay, with that I'm done. I have to acknowledge the Ministry for Economical Affairs and Energy and the Bundestag and my project partners here. And with that, I'm done. I'm open to questions.
Are there any questions from the audience here, or that matter in the chat or online?
Have you tried the two maybe another tests or separately from the one that you showed us?
Yes, so we did external aerodynamics extensively. So I had a really good master student who is like was the member of like a competition car student initiative, a little bit like Formula Student, if you know that, but for solar cars. So their range was their goal was just to be as slick as possible and drive through Australia this summer, which actually they did. So we did stuff there. Then as well, ducted flows. Some people used it also for estimation of turbulence parameters. I'm not entirely sure what came out of that. And also, I think a postdoc from J.R. Martin's group also used it extensively and compared it, I think, to their DA foam solution. So there have been plenty of applications, and if you go to the it doesn't work anymore, but if you go to the website, you will see a list of applications. Yeah, it's fine. But we haven't done compressible, I think, or we've done it, but not like in a way where it's actually matters, because we didn't have the application.
Yeah, that's okay.
Yeah.
Any other questions? Can I ask?
Mm-hmm.
Am I understanding this? You're doing the geometry by cell blocking, so you've got a function which is blocking out flow.
For the topology, yes.
Right, okay. But for the heat exchange cases, doesn't that solve the problems you identified? By definition, you'll have the same topology on the interface, and you'll basically have two meshes, one of which will be for the solid phase, which will be 1 minus alpha, and we'll have all the properties there.
Yes, but if you do the topology, well, basically we would say the solid is fixed, and we would be able to add additional material in the fluid phase.
But if
that has to have the properties of the copper, for example, of the other stuff.
Yes, but if you are using a blocking technique for the fluid, you could have the same overall mesh domain, use a blocking function of 1 minus alpha to the solid phase.
Yes, yes.
And by definition, you'd have the right properties.
I think so. I think that's also what she did yesterday. And I thought, oh, no, why didn't we do that? I think we haven't tried it.
This is why we come to conferences.
Yeah. And also, I think at that point, probably you would have to do some inverse boundary because just porosity stuff is not that great.
No.
You would need to have a lot of finer mesh to get the resolution right.
Okay, well, thank you.
Thank you. My name is Mirza Popovac, Austrian Institute of Technology, and I prepared this presentation on the continuous adjoint topology optimization with robust design variable update, which is pretty much everything you heard already, except for this small last bit. This is not it, but this. So yeah, I will repeat most of what you heard already. In principle, as you heard yesterday on my splash talk, we are interested we at AIT, I mean, working with need to work with the robust, which means most of the time, yeah, simple and stable tools to apply to different applications. So the robustness stability is the key word, I would say, in my work. And yes, the adjoint optimization method is obviously a very powerful tool. Therefore, yeah, much used, so much so that in OpenFOAM releases there are 2 solvers. One is adjoint shape optimization foam, which is doing not shape but topology optimization, but it came first, and then the adjoint optimization foam, which is much better, I would say, better maintained, better developed. Yet you see where I'm going to. I'm not using this one for for this presentation because the adjoint shape optimization foam is simpler written. It was exemplary, of course, and therefore just there probably for historical reasons. Nevertheless, I use it because it's just easy to show what I was doing. And the thing is, for the topology optimization, very often the constraint for the volume of the cells occupied by the porosity is required in the development. So it's one thing that is to be considered. I will use this feature later on in very simple manner. And on the other hand, if you use what is typically, well, again, as a simple case used, for the steepest descent, the update of the design variable, which is simple method, nevertheless present in the code, for example, you need to specify some parameters, like the step of the updating, which, yeah, you have to somehow estimate. And that's not easy thing to do. So what I was thinking is to make use of the example. So in the Otmar paper, which is actually replicated in the adjoint shape optimization foam solver, they are showing the example. You solve the primal velocities, you get the adjoints. From there, you calculate sensitivities, and voila, this is your porosity field, which leads you to the better objective function. But I thought, why not using this feature that my blocking cells are blocked and treat them as a mask. So yeah, this is this is what I want to present now. But before that, of course, a little bit of math. You saw this already, but I have to go through it. It's in the paper as well. I'm just saying, so for the continuous adjoint topology optimization as implemented in the adjoint shape optimization foam solver, which is suited for the ducts shown to the right. Okay, you are starting with the problem. Okay, let's minimize our objective function such that the constraints are fulfilled, and the constraints are transport equations. So momentum, continuity, all fine, and we are introducing our design variable in the form of the porosity, Darcy porosity, and that's our design variable. And then, good, we have to prescribe some boundary conditions for our transport equations, inlet, outlet, walls, and in order to solve this, to minimize the objective function, we expand the function with the Lagrange multipliers, and then comes the math, which of course we are happily skipping, but in the end you are getting the equations which are similar to the primal, yet in the case of momentum, for example, yeah, we all know there's a convection which is in the direction opposite to the primal, and there's additional term which they call the transpose convection. So that makes it, of course, difficult to solve. Nevertheless, we again have our design variable alpha in that equation too, and for a specific objective function, we can derive the boundary conditions, inlet, outlet, and walls again, as given here from the paper. And yeah, this is all fine and known. You've seen that already third time now today. And right, once we have primal and adjoint equations, in the case of topology optimization, there's no shape motion. The boundaries remain unchanged, and we need this to obtain the sensitivity field, which is used to update the design variable. Right. So it looks a little bit like this for the available design space. In each cell, I calculate the sensitivity, which is, again, from the textbook example, used in the steepest descent mode to go down the curve from the initial value of the design variable down to the optimum one in given step size. Well, again, if the step size is too small, then you are walking towards your optimized value slowly. If you use too big a step size, you can jump back and forth, which is a little bit unstable. But in principle, from these sensitivities calculated through the primal and adjoint variables for each cell in your design space, you produce something like, in this case, it comes from below, it leaves to the right, to, let's say, something above. That's okay, the corners are blocked, and we are happy with this. So in each update step, we are iteratively updating our design variable. But my thought was, as I said before, I know what my design variable should be. So once I, starting from the initial guess, solve the primal, once converged, compute the objective function, go to the adjoint equations. If they converge, get my sensitivity. I have the sensitivity, which I need to update the design variable field. But I mean, I know where I am. Like, is it free or already blocked? Let's say it's free. I want to block it if if that cell doesn't contribute to the minimization of the objective function. So I know what is my end value already. I know that I want to come from 0 to 1 if the condition is fulfilled through the sensitivity function. So I thought, well, this is an example of sigmoid function performance, like one given so, in which I have two coefficients. One will tell me around which point I'm switching from 0 to 1, and another coefficient will show, okay, with which steepness, so how fast. Again, playing further, I can combine these two and write it in a below manner, such that, again, I have the point around which I'm switching from 0 to 1 with the steepness as predefined. But if I have a freedom, of course, if I impose my constraint to select one of them, and my constraint is, as I said before, the occupied volume constraint. So in the end, what I'm doing, next step, of course, this is all just explained a little longer, but in the end, I will be using my in a stepped manner. I won't be going actually through the sigmoid at all. I'll just check yes or no, greater or lower than, go through the cells, specify my alpha in an initial guess from the maximum value, and then maximized it will start from 0 downwards. But in the exponential space, so to cover more decades, not linearly, and then check, okay, for a given value of sensitivity, do I fulfill the volume constraint? Yes or no? I'll take a few loops. In my experience, let's say 5, and reach the limiting value. So as I said, okay, here, it does work somehow. Starting from the maximum value of the calculated sensitivity, as expressed in the normalized threshold in decades, I'm going all to the point until which my volume constraint is fulfilled. Like I said, I'm not updating and waiting to get to this value, and I'm fulfilling this, I have to admit, arbitrary, yet with engineering logic backed requirement that the blocked volume is defined. So now this is how it works. On the example of the tutorial case, which is provided, this Pitts daily case, again, I have my primal velocity, whatever I calculated as adjoint will give me the sensitivity field. And yes, this bit here is with what I have to update my design variable. And then I'm selecting what is the relative volume. Of course, I can normalize it with the total one. And select only a little bit or more or everything that is being calculated. And so it boils down to the very simple idea. I'm picking from the sensitivity field the values as I prefer, and I say, okay, I'll just pick the highest one up until the volume is reached. And again, this example shows that if I am to select one point which will help decrease the total dissipated power in the Pitts daily case, it's the point behind the step. Well, not very useful. But yeah, that's what tutorial cases are for, just to show the principal idea. This is more example that I needed this for. So I want to distribute the flow coming from a pipe below to the two slits above. And yes, okay, this is the let's say our developed solution. The flow will, of course, hit the back side and then split sideways, but then it has to somehow bend up before reaching the outlet above. If you try to solve that with the available adjoint shape optimization form solver, depending on the step, the update step you select, you can have something like this. The one to the left is obviously the lambda updating step too low, which means, yeah, you get these green segments, which means it still is evolving the field, because in the end, for the topology optimization, you cannot put a little bit of porosity, either you put or you don't. So it has to be red in the end. The middle one is obviously something like you would somehow justify or expect. But if you go too high, you start having some rips or whatever, which is obviously some sort of instability in the update itself. Instead, with this explicit update with respect to volume, the required occupied volume, I'm having the solutions like this. So I calculated this 3 times with different set values for the occupied volume. And of course, if you select a little bit of the volume to be occupied, he will choose only the hardest ones, which is so here I'm showing the calculated sensitivities. He's obviously seeing it the strongest here at the entrance. So he wants you to push forward, don't move left or right. This is fine. And then along the back walls, and then you can, now it's difficult now to see, but once it turns up, there is a bit that you also don't need here because he's moving from the back towards the end. So, okay, if you increase the relative volume, yeah, he will capture some of it through the porosity, so you get a little less pronounced sensitivities and more filled with the porosity, which means, yeah, now, okay, fine, completely block this upper bit of the incoming section. And if you go to higher values, yeah, so you can also freely, this vertical bit, you can also cover from the inner part, so he just let him move from the back or something like this. Interesting is to see, okay, for the same mesh, the mesh I was playing only for the in the primal solution, and then didn't go for the mesh refinement or anything. If you impose more, if you allow for more volume to be occupied, you can better reduce the objective function, which means, yeah, of course, he's better streamlining, but in the end, that doesn't matter. The topology optimization is anyhow, the idea is to guide you with the concept, the fine tuning or final surface you would forge out yourself differently, either to shape optimization or with other constraints, mechanical constraints you have. But the idea is here in all 3 cases, starting from the initial field without any porosity inside, you see that in all 3 cases, it doesn't make sense to update more than 3 times. So he solves primal adjoint, puts in some sand, then he updates velocity primal and adjoint and puts another sand portion, and after the 3rd time, you see he's getting the plateau more or less constant. Yeah, this doesn't work. Okay, so in all three cases. Another example which I found useful to show here, in this case, I can also, because this is kind of post-processing, so I can freely select. It's not in the equations upfront. I can select where to take my sensitivity and update the design variable. And where not. So in the case of this, let's say, pin plate cooler, the flow field looks like this. Yeah, it comes in and then passes through the pins and then leaves to the back. And if you would want to optimize something like this, I guess you would play only with the entrance and the exit section, while the pins itself you would optimize probably differently, separately, not on this scale. But in this case, yeah, you have what you have, and you are just asking yourself, okay, can I get it a little better just by improving inlet part. And as I said, so since this is anyhow the update is up to you to decide how and to which extent to use. I can set a zone and I say, okay, yes, only sensitivities in this region are used, and the flow field or adjoint the design variable field is updated. So yeah, this is more or less the idea. Very simple, but very long way to say. I used for my topology optimization only those parts that I somehow handpick through the parameter which does make physical sense. So you see what you have. I want 5% of this volume here to be filled with some sand in order to get my, in this example, power, total power dissipation. I didn't talk about the frozen turbulence assumption that is in the adjoint shape optimization foam, or other objective functions, anything. I'm just using what is there and playing with the update, which is actually explicit design variable update with volume constraint implemented directly. It's simple, of course, and straightforward to implement, and the numerical performance is, well, satisfactory. It doesn't get any worse than with what you have without, or actually just solving primal and adjoint as they are. So yeah, that was my talk. Thank you. And now I have some questions.
Questions? Yes.
Thank you for that. I'm afraid I may have been looking rather strange at all of this, because it seems the approach of having an objective function now changing and steering effectively what is in some of your applications of ductwork appears to be analogous. Well, it seems to be the process that actually occurs in honeybee clusters as they actually generate ventilation channels internally. And so the actual mathematical approach there you've got with an objective function, I was just wondering, so that really, so the fact is that could be almost anything. Like in my application, it could be the CO2 concentration, it could be humidity, it could be temperature driving that that change of the design.
Absolutely, absolutely. But we already heard this. In the continuous adjoint, you have to derive all these equations. Derive from the primals, so temperature and concentration, everything. Derive these adjoint, which can get quite messy. But once you get it, and then implement your boundary conditions, which gets more messy, you will get the equations you are solving and obtaining directly this, what is called sensitivity field, the field where you intervene in order to help yourself. Yeah. This is it.
Yeah, it's just a case of the field of honeybees is actually evaluating all of those things in those points, and then doing a movement which is the same thing as you're doing.
Yeah, I can guess that the bees are adjoints feeling these changes and make their structures accordingly. Yeah.
The scientists have a technique called colony optimization, which I think may parallel very much what bees do, and might be worth investigating as an alternative approach at some point. So.
Probably more like a global optimization.
Yes, yes, that is a variable optimum search. Yes, of course.
Question. This idea of controlling the step of the update, is it applicable to, like, let's say, quasi-Newton methods for the update of the data instead of only steepest?
This is the point. You can have different update methods with Jacobian left, right, up and down. It would get better. But my first question is, do I need this in this case? I just want to know, is it 1 or 0? If the condition is satisfied, I will take 1 without these intermediate steps.
I think this is what Carsten Wortmann did really back in the days. I'm not sure if this moved over to the OpenFOAM version, so I've seen the old and it's all like a little bit handy, right? Because the sensitivity you calculate is not actually sensitivity used, because you kind of shift it. It works, but like mathematically it's strange. So question, do you always need to prescribe the volume constraint, or can you just say, okay, give me the best fraction?
Okay, could you summarize questions for the
all right. So the question was if the required volume needs to be specified, or it can search for the best. Well, this I wasn't playing with this, but yeah, obviously you can search whichever condition you want. You see that this condition came into this sigmoid. How do I fix my sigmoid function? So whichever strategy suits you, this is it. This is, like I said, the straightforward. I will just say if sensitivity higher, whatever I say, take, otherwise leave. But yeah, I can guess better strategies than that.
The equation, because when we are dealing with volume constraints in topology optimization, so we developed several tests with different values, and we compare the objective function optimization. So for example, you say, okay, let's apply a 30% volume constraint of this topology, and you see the objective function is 1 value, yes? And then you can make a different test with another volume constraint value that says 50%, and you see the objective function again, and if the objective function is improved, therefore you will stay with that volume constraint value that is applied, for example, in this case, 50%. So that's like how the process is made. So it's a parameter that
can slide.
And we compare it with each objective function along the
yeah, okay, but that for you is an additional parameter function.
Yes,
if you do the standard upgrade and just say, okay, I cut off everything below 0, then you get that for free, basically. Because it will just search the optimal value, kind of. But then, of course, if you have something where it really wants to fill up all the volume because it's somehow best, then of course you have to constrain.
The idea could be also to make this implicit. So you put this constraint in equation, and then this would be the way that he finds the solution itself.
Yeah, that would be better to confirm, at least if you differentiate. Because then this constraint is actually part of the problem formulation.
You can propagate it back and forth. Yeah. Yeah, this is why I said this is explicit. I was referring to this explicit constraint of the volume, occupied volume, but yeah.
Are there any other questions? I don't see anything online, so can we thank?
Thank you.
Good morning, everyone. My name is Themis, and I'm a PhD student at the National Technical University of Athens in Greece. And in this presentation, I will show a method developed by our group, the Parallel CFD and Optimization Unit, which is used to perform the Adjoint-Based aerodynamic shape optimization for turbulent flows in the presence of uncertainties, using the method of moments and the projection technique, which is one of the focus points of this presentation. Yes. So The main pillars of the presented methodology are the adjoint optimization library of OpenFOAM, which was developed by our group and made publicly available via OpenCFD, an uncertainty quantification method called the first order second moment, or FOSM for short, which computes the two first statistical moments of a quantity of interest, the mean value and the standard deviations, and a projection technique, which we use to reduce the cost of the optimization. Putting all of this together, we get the projected FOSM method, which has a comparatively low cost and was developed in the in-house variant of the adjoint optimization library, with which we perform shape optimization under uncertainties. More information can be found in these two publications. And in this presentation, I will briefly introduce the projected FOSM and describe a shape optimization loop with this method. Finally, we will just see some applications in turbulent flows, which were modeled with the Spallard-Almaraz turbulence model. And wherein the uncertain variables are related to the flow conditions. Let's take a look at an adjoint-based optimization loop quickly. Assuming that there are n design variables B, m uncertain variables C, and f is a quantity of interest, such as drag, which we wish to minimize. In case there are no uncertainties, this loop looks like this, where we only need to solve the flow equations, compute the objective functions, then solve the adjoint equations, and compute the required gradient. The cost of this loop is equal to two equivalent flow solutions, assuming that the adjoint equations cost as much to solve as the flow problem. We will use this EFS as a measure of the cost throughout the presentation. And now, in case of optimization with uncertainties, this loop changes, and the objective function is defined as a weighted sum of the mean value and the standard deviation scaled by some factor. So the statistical moments of f, the quantity of interest, need to be computed, and then the gradient of this expression with respect to the design variables to update the design variables. So these two blocks we will take a look at in the next slide. So according to FOSM, this method uses a Taylor expansion about the mean values of the uncertain variables. The second order terms are excluded, and with this expression, the mean value and the standard deviation are given by these two equations. The objective function is then computed, and finally, for gradient-based optimization, we need to compute this term over here. Notice the existence of these two terms, first order gradients of the quantity of interest with respect to the uncertain order design variables, which in case we have an adjoint solver available, these are easy to compute, but then we also need to compute the mixed derivatives, this quantity over here. For second order derivatives in general, an efficient way to compute them is with a combination of adjoint and direct differentiation techniques. And in the case of the mixed derivatives matrix, the computation of each individual component, the cost of it scales with the minimum of the number of design or uncertain variables. So the main idea in projected FOSM is to take a look at this equation, and instead of computing all the individual components, compute the projection of this matrix onto some vectors, a vector z directly. So how is this done? Remember that this is the expression we need to compute, which in the cases that follow is given by this almost simple equation. Some familiar terms can be seen here, such as the pressure or the stresses. And the rest of the terms with the overhat above them denote any quantity phi that is first differentiated with respect to the uncertain variables, then projected onto z. So this, the projection of these mixed derivatives is actually a function of the flow variables, the adjoint variables, and they're differentiated and then projected onto z counterparts. So PDEs must be derived for these two additional sets of variables. Now, to just include all of the equations here would be overdosing this slide with equations. So we'll just work with an example. And for me, the simplest equation is the continuity equation. It's in here at the top. The second one is the adjoint continuity equation. This looks very similar. And what remains to be done is differentiate this equation with respect to C and project the resulting equations onto Z. So imagine now that we have also the momentum equations and any other governing PDEs that accompany them, and we do the same. And in the end, we simply need to solve 4 systems of equations in order to perform an optimization loop to include the uncertainties in the optimization loop. So this is the cost per optimization cycle with uncertainties with projected FOSM, assuming that there is only one quantity of interest. So to analyze the cost a little bit more, in case there are no constraints and we optimize for the mean value of the quantity of interest, the standard deviation is not involved and thus no mixed derivatives need to be computed. So the cost is equal to 2 EFS only, a solution of the flow equations and the adjoint equations. Now, in case we include the standard deviation in the objective function, without using the projection technique, this cost scales linearly with a number of uncertain variables. However, using the projections, this cost is equal to 4 EFS only, the solution of the additional systems that I showed you before. And this does not scale with the number of uncertain variables. It is independent of the number of the design nor the set of variables. In case there are flow-related constraints, assuming that there are k flow-related constraints, these costs are added to the above. So in the cases to follow, we will have two uncertain variables, the far-field flow angle and velocity magnitude, and there will be two constraints imposed in all of them. So the cost of the optimization will be equal to 4 equivalent flow solutions for optimizing the mean value, and 6 when optimizing a combination of the mean value and the standard deviation. So let's move on to the applications. In the first one, the NACA 12 airfoil was optimized in the presence of uncertainties in a Reynolds number of 1 million. You can see the values of the uncertain variables here, the mean value and standard deviation on the left. Two optimization runs were performed, one for minimizing the CD and one for minimizing the CD plus 3 times the standard deviation. The airfoil was parameterized with the parsec 11 technique. The trailing edge was kept fixed, so we're dealing with 10 design variables only. And 3 equality constraints were imposed for the lift and the pitching moment coefficient and the cross-sectional area of the airfoil to remain equal to their initial values, with the exception of the pitching moment coefficient, which for which the target value was set equal to 0. So for the lift coefficient and the pitching moment coefficient, 2 adjoint solvers need to be employed. Additionally, on top of the one for the CD. So with a mean value of CD as the objective function, within the span of 60 optimization cycles, this was reduced by 1%. However, the standard deviation increased by 6.5%. For the run with the standard deviation in the objective function, this increase was mitigated, but at the expense of much lower reduction in CD. From the two optimized shapes, you can see them here compared with the initial airfoil. The optimization mostly altered the pressure side of the airfoil, and you can see here the reduction of the pressure gradient close to the leading edge on the section side. The dashed lines on both of these plots, the pressure coefficient and the skin friction coefficient correspond to the section side. And you can see here the effect that the optimization had on the coefficients along the pressure side of the airfoil. Regarding the constraints, here you can see the pitching moment coefficient plotted versus the drag coefficient. Each point corresponds to a different far-field flow angle. And the point here, starting from the NACA 12 airfoil, you can see how it was reduced to 0. And on the next plot, you can see the lift coefficient. It remained practically equal to its initial value. And the drag was reduced in the close proximity of 4 degrees angle, which was the mean value of the far-field flow angle. So after satisfying these constraints, an airfoil with slightly less drag was produced. In the next application, this time the NACA 4412 airfoil was optimized for maximum lift. And you can see the Reynolds number and the mean values in standard deviation of the uncertain variables. The airfoil contour was parameterized with NURB squares, and 2 optimization runs were performed with these 2 objective functions. Here, the same types of equality constraints were imposed, only CD and CL are interchanged with the previous case. And the target values for the constraints were set equal to those of the NACA 4412 airfoil. After 40 optimization cycles, with mean CL as the objective function, it was increased by 1.9%, but at the same time, the standard deviation also increased by 5%. So in case this is undesirable, just by including it into the objective function, at the end of the optimization, it was only increased by 1.8%, but this had the outcome, but this also resulted to a less increase in CL by 1% point. At the end, all the constraints were satisfied, and the last application where a different airfoil was optimized in the same types of flow conditions with the same values for the uncertain variables. And at the end, the solution is compared to the NACA 4412 airfoil. The quantity of interest is the drag coefficient, and the following equality constraints were imposed where the target values were set equal to those of the NACA 4412 airfoil for the purpose of comparing the final optimized solution. With the mean value of CD as the objective function, it was reduced by 4% compared to the initial one, and the standard deviation was decreased by 3.11%. With the weighted sum as the objective function, the drag value was decreased by 3%, and the standard deviation by 4.2%. In all cases, below the values of the NACA 4412 airfoil. So, to conclude this presentation, the cost of the projected FOSM, the unconstrained optimization loop, is equal to 4 equivalent flow solutions, and this cost is independent of the number of the design or the uncertain values, just as we saw previously. Now, provided that the available adjoint code includes the adjoint to the turbulence model equations, the projected FOSM can be used in turbulence flows in a straightforward manner, and I can only speak for continuous adjoint. This is the one I have used, one I know, and for that, the extra effort to develop the robust design optimization code with projected FOSM is reasonable. The additional effort for programming, and especially in the adjoint optimization library, the modification of the code to solve the additional systems of equations could be easily done. So thank you for your attention.
Are there any questions?
Yeah.
If I can get you to repeat the question for the benefit of the online audience. Yes.
Do I understand right? This methodology can be actually used also to calibrate parameters like the inlet profile,
Calibrate them in a sense.
Well, you're measuring some value somewhere in the domain, and you want to know what is the let's say parabolic profile of inlet.
I'm not sure it can do that. How would you formulate this? Like, you want to measure a quantity in the flow field. This is what you described, but then use, for example, the gradients to find out the profile that caused this quantity to appear. This is what you mean, right? So I'm guessing that the flow profile somehow would be part of the design variable of a problem, right? So you would formulate your problem like this. I don't think this would be part of the uncertainties. In this sense,
it's an inverse uncertainty problem. It's what if you can measure the uncertainty in your measurements, you can infer the uncertainty on the inputs, I think.
So of course you could do it if you had gradients, but in terms of the formulation and how I presented it, it would be like the design variables would be the ones that would be changed and adjusted, and the uncertain variables the ones that we only associate a distribution with them and propagate it within the flow field. But it wouldn't be done. I wouldn't go with this methodology specifically, just a simple flow problem and then adjoint solver. Just a gradient to back propagate it.
No, as I meant, there would be some scattering in the measurements as well. This is where it's coming from. But okay, I see what you mean.
Yes, this is how I understood your question, like how to fix the profile to get that value.
From the thing that has some distribution.
But if the profile was somehow part of an uncertainty problem, which you would just propagate it there, yes, it will be included in this formulation.
That's good to ask that question. So thank you for answering it in advance.
Yeah.
Is there another? Yes.
In some of the plots, I noticed that the sensitivity of the red curves, I think it's all the standard deviations, seems a lot more junky than some of the points. So the reason that the blue, this regular version is a lot smoother.
Yes, I noticed this. This was mostly in the problem that this happened. Let me show you. Okay, doesn't matter. Okay, yes, it's okay. In that case, there was this strict constraint on the pitching moment coefficient, which required it to be equal to 0. So in that case, most of the, let's say, effort for the optimizer was to satisfy the constraint. Now, the mean value, the standard deviation was much more sensitive to changes in the design variables. So putting all of them together, its update of the design variables disturbed the progression of and the convergence of the objective function. So it was mostly the optimizer trying to put back the constraints in place.
Do you think there's any issues with actually, say, create the airport
on the final solution? Not really. I actually, if you would let it more, you would see it converging. After that point, which I cut it, the how can I say, this thing stopped. It converges.
Thank you.
Are there any other questions?
Thank you for the presentation and participation. Quite follow your work of the research team. I've seen that you there have coupled shape optimization and topology for internal flows. Are you thinking maybe coupling this internal flows optimization as well?
Currently, I don't have problems in mind where it could be used right now. Like perhaps this was one idea for internal flows. I was thinking to move mostly to geometric uncertainties and stay in external aerodynamics with these. So this was the idea. Move on from this one and to geometric uncertainties.
There are no further questions, and I can't see any in the online chat. So can you join me in thanking the final speaker and all the others?